Hello, computer vision class. Today I'm going to be talking to you again about using automatic tracking for in situ recordings of marine larvae. So this is my outline from my last talk, and what I talked to you last time was focusing mainly on the context of the work, specifically where are these recordings coming from, what's in the recordings, and why am I interested. I also talked to you guys a little bit about the potential problems I have to account for when I'm developing a tracking procedure, and also what methods I'm using in my tracking program that are going to help me deal with those potential problems. This is the drifting in situ chamber, or the disc. On the left you can see a diagram of what the disc looks like. In the middle you can see the disc being deployed, and in the far right image you see an image of the chamber of the disc that's taken from the video camera mounted on the disc itself. And I won't get into too much detail about this, or the sensors that are on it outside of the camera, as they were talked about last time. I will, however, review the Discus, or the Disk User software, that was developed in conjunction with the disc. And I will stress the point that the bash script, which integrates Discus, opens up ImageJ to perform manual tracking of the larva through each frame of the video data, something that's not very fun. But to remind you of what it looks like, this is a very ideal case where there's not much turbulence, there's not much light or sedimentation, and the larva is pretty clear to see in the image. Not all trials are like this, or else it would be much easier to do. After the tracking, I'll remind you that you get the XY coordinates, but we're not really interested in the XY coordinates in some static artificial square arena, because that's not what the tank is, or the chamber rather, and that's also not what we're ultimately interested in. So the first thing to do is to transform them to polar coordinates, and once we have those, we bin the XY positions into 5-degree histogram. And so on the left you can see before we correct for the compass that's mounted on the chamber. And on the right you can see after we've corrected for the rotation of the chamber, which we get from the compass. And we can then perform Rayleigh's R statistic to determine what the most preferred direction was, or what the orientation of the larva was. But this is all a little bit besides the point. So I'll get back to what this project focuses on, which is automating the tracking process and replacing the bash call to ImageJ for manual tracking. And we're hoping to deal with some of the problems that previous attempts have encountered, which are 1. Marine snow, 2. Lighting changes throughout deployments and throughout a series of deployments, obstruction by the chamber, and also artifacts created by the chamber. So we created some field adaptations which we hope would deal with some of these. The first two in red dealing with light, and our solutions are to deploy deeper so that the light is less intense and thus the variations are less significant, and also to deploy mostly at night with fixed lights attached to the instrument. In blue you can see things that we've added to deal with the artifacts and the structure of the chamber itself, which are to replace the surface float with a buoyancy engine, and also to make everything that's on the chamber or the disc itself clear so that there's no visual attractants for the fish. The first method that we'll be using, beyond field adaptations, is background subtraction. And I talked about this in a little bit of detail in my last presentation, so now I'll just remind you that for pixels that do not change for more than some threshold value, they are turned black, and pixels that are changing are turned white. So we create a binary image, which is much easier to track than the very complex red, green, blue images that we get originally. So I showed you this last time, but this is what it looks like when we're doing this. In the top left we have the frame itself, in the bottom left we have the background that's calculated, and in the bottom right we have the binarized difference image that shows clearly that the only thing moving inside the bounds of the chamber is the fish itself. So this is pretty useful because we can get rid of a lot of things that we're not interested in the frame. For example, the structure of the chamber, any slow-moving debris that's in the frame, and also any distant, near the surface organisms that, because of their distance, appear to be the same size and in the same location of the larva. And while this reduces the number of salient points, there are still salient points that are not of interest in the image, which means we do have to develop a fairly complicated and sophisticated method for tracking the larva with the presence of these other white salient points in the binary image. To do so, we make a call to DLT-DV3, which is a tracking program that's been developed by the Ty Hendrick Lab at University of North Carolina, Chapel Hill. And what this does is to initialize tracking by first selecting a known point on the larva through several frames. A model is then fit to these points and is used to predict the location of the point in the following frames. He suggests to use an extended Kalman filter, but as you can see in this middle arrow here, that it is possible to select other types of predictors for where the larva will be. You can also vary the search area size and the threshold for whether or not something is a good fit. I've kept the graphic user interface because it's easy for troubleshooting. Now, what this program does when it fails to find a match is that it prompts you to select in the object of interest again, essentially re-priming that Kalman filter, or whatever the predictor method you're using is. So, this is the slide I showed you last time on what remains. I still had to obtain appropriate video data, something I haven't done, to fine-tune parameters for background subtraction, I have done, to write my own auto-tracking prediction method, which I haven't exactly done, but I've modified some of their code to make it more suitable, and I also had to deal with some special cases for larval behavior. I thought I might get rid of the graphic user interface, but after talking with my advisor, since we do sell the disk, and because Discus is open source software, we've decided to keep the graphic user interface. It might make it easier for other people who are using variations of the disk which are not exactly like ours, and in varying environments, to be able to track under different circumstances than their own, where perhaps the ideal parameters and tracking methods would be different than the ones that we find to be ideal. The second to last point on this page, which it has two questions relating to specific circumstances of larval behavior, I'm going to talk about in a little bit more detail later in the talk, so you don't have to worry about those for right now. Instead, what I'd like to do right now is to return to the original outline. Because of a question Tommy asked at the end of my last presentation, it became clear to me that I hadn't really explained the motivation for me doing any of this, so I thought that I'd spend at least a minute doing that now. The CMS, or Connectivity Modeling System, is some open source code that's developed by a scientist in Claire Paris's lab at Erasmus. What it does is to combine oceanographic models like HICOM or ROMS, which have the ability to give you the three-dimensional velocities of a point anywhere on the grid of whatever ocean you're looking at some resolution, and combine those with biological parameters of the larva of interest. For example, where does it spawn at? How long is it in the water column before it tries to settle on a reef or another substrate? Does it have strong or weak swimming abilities? And possibly, is it stimulated by environmental cues? And when it's stimulated, what's the behavior that's a result of the stimulation? And when these things are combined, we can figure out a larva that spawns in this location ends up going to this location where it settles out. It's useful for all sorts of things like resource management or designing marine reserves that are most effective, or for even just giving fishermen heads up on where to look for fish in the future. The model here just shows a fish that's stuck in an ocean eddy. Ultimately, the model determines velocities of thousands of different particles, which is a very heavy process, so if you're wondering why Pegasus might seem slow on a certain day, we apologize. Also important to remember is that it's a biophysical model like I mentioned before, which means that the results of disk studies help to inform the biological components of the CMS so that they can more accurately model larval dispersal. So, for example, if a larva is passing by a reef and it gets within some distance from the reef, is it now able to hear the reef? Does that cause it to swim in the direction of the reef? Does it cause it to swim downward and maybe locate a more favorable water mass that's moving in the direction of the reef? All of these disk studies answer small questions like that, which make small changes to the CMS, which probably in the end make a small difference to the trajectories that the larva travels. The second thing that I want to talk about is, how's it going so far? So, let's demo. First thing I'm going to do is to pull up MATLAB, as well as the script for the tracking. And before I do anything else, I'll remind you that all of these components, the tracking, the statistics, and this automatic tracking, are linked through bash script, which means there's a little bit at the top of the script just to make sure that it's looking for things in the current directory that bash is dealing with other things that have already been output from other programs. The next step is going to be to select the region of interest of the frames. And the way we do this is to pull up the first frame of the video, to select 3 points on it, to do a little bit of high school geometry, and then to come up with the circle that's the region of interest. We can then make that circle a mask so that for all of the rest of the images that we'll process, only that circle of pixels is going to be shown or processed. We then convert the original video from .mov to a .avi format without making any changes to it. What this does is just put the original video, unprocessed, in a format that the tracking program likes. The next thing is to do adaptive background subtraction on each frame, and I described that a little bit here and more in detail in my last presentation, so I won't go into detail other than to mention that there's 2 outputs from this. One, which is the red, green, blue background subtracted frame, and also the binarized background subtracted frame. And those can both be used for the tracking, but I'll talk a little bit more about that later. For now, let's just run the script. You can see that right away it pulls up that first frame, and we're going to select 3 points on the chamber, the outer wall of the chamber, and it's going to draw the circle. We're going to say that yes, that circle looks good, and then we're going to wait. Right now what it's doing is taking all of the MOV frames and converting them to an AVI movie. So we'll wait, and we'll wait, and I may eliminate this from later versions depending on how useful this AVI movie actually ends up being, because we're still waiting. Okay, so now the background subtraction is occurring. You can see up at the top left there, shows you how fast it's going, and we don't really want to wait that long, and luckily I've already done this. So I'll just note that it processes the frames individually, and then that little bit of code at the end is going to put all the frames into an AVI movie. But for now, let's just close out of that, and let's load the tracking program. We'll initialize it, and you can see that it prompts you for how many videos you have to load. And this relates to some of the things I've been talking about, which is that eventually I hope to have 3 videos that load. 1, which is the unprocessed video, 2, which is the red, green, blue background subtracted video, and 3, which is the binarized background subtracted video. And there's a calibration part of this code so that it can take all 3 of those videos and use the data from all 3 of them to track. So if tracking could be successful in one frame, or one video source but not another for that frame, it will use whichever one's successful. So hopefully that will make things better in the future, but I'm not going to try it until I get the right data. For now, I'm just going to load the one I've had the most success with individually, which is the binarized background subtracted data. Here are the controls. Skip over the first frame, because that is all black because it's the ultimate background. We're going to know that we only have 1 point, a larva, that we're tracking. Select automatic tracking, and first order polynomial prediction method, which is the one that I've had the most success with and added my own bits of code to. We'll set the threshold for what is a good fit a little bit lower, and we'll make the size of the search area a little bit smaller since the larvae are pretty tiny. You can see here that we can scroll through frames using the arrows. We can press F and B for forward and backward, or we can simply type some frame that we're interested in right here into the box and go to it. So you can see in this one the larva is right there, and I know that from previous experience, and we'll start tracking it. It goes through a couple of frames, loses it, we press again, and it starts tracking it again. And we could do that through all 2,000 frames. But for now, I'll just let you guys know that that was about 40 frames that it tracked through in 2 seconds, requiring 2 manual interventions. So there's room for improvement, but it's worth noting that going through 40 frames with manual tracking would probably have taken 7 to 10 seconds per frame, so it's already a massive improvement from what we have currently using manual tracking. When it saves the data, which is an option at the top, it will save it in XY coordinates, but right now we're not interested in saving. We'll just close out of MATLAB, and we'll go back for some final notes. So, what's still left? I told you guys that I'd answered one of these questions, but not the other that were listed earlier. The question of what happens when the larva doesn't move has been dealt with. So anytime the larva doesn't move, and it can't find any salient points in the region, it will simply just keep selecting the point that it had before and skipping through frames until it gets to a frame where there's a salient point which matches the Kalman filter prediction area and also has a lot of the qualities of the match from the previous successful match. The second question I haven't dealt with successfully yet, and that's when similarly sized debris appears above or below the chamber, right in the area where the Kalman filter or first order polynomial predicts the larva should be. So I'm still working on that, and hopefully I'll have an answer besides manual intervention fairly soon. The most important thing I've yet to do is obtain appropriate video data from the field. My lab mates are still in the Bahamas right now. They'll be back next week, so hopefully this will make a big success, or a big increase in success of the program. Some other things that I want to do eventually are automate the detection of the disk chamber so that you don't have to select those 3 points, and like I mentioned, to enable simultaneous tracking on 3 videos, the unprocessed, the background subtracted, and the background subtracted binary. Any questions? Oh wait, that's right. You can't ask any questions. Sorry. Too bad.